Hi, welcome to module 32. In this module we are going to learn state assignment. So state assignment is a very important part, and it is good to know how to do efficient state assignment, at least for small circuits which you do by hand. So state assignment as a process, it comes in the it's an intermediate step. So you start with a state diagram, and the state diagram captures the functionality. So when you have a particular problem, the state diagram that you come up with captures what the input output relationships are and how the states should transition. The next step that you take is take the states and you have to assign the bit vectors associated with it. So far we have been doing things like for S0 we will give 0 0, for S1 we will give 0 1 and so on. But unless you do that, you cannot go to the next stage where you go and look at the excitation tables of the flip flops. So if you have only the symbols for the state names, you cannot operate them and you cannot get bit representation. So state assignment is a binary encoding. You start with your representation, you start with your state diagram, and for each of the states you come up with some kind of encoding. You start giving bit vector names instead of symbolic names, and once you have that, you can then go and look at excitation table of the flip flop, arrive at input output relationship and so on. So we were so far just doing one state assignment. So we came up with something and then said, okay, if we do this state assignment, this will be the circuit and this will be the output and so on. But it's quite likely that your state machines have multiple state assignments which are all very competing. So what I mean by competing is that in terms of the number of gates that you have, things could be different. So we'll see a quick example and see what the state assignment can do to different kinds of sizes. So let's take a small example. This is a state machine. So let's forget the state diagram. We have a state table, and in this state table there are 7 states from A to G, and we have the next state as well as output marked in the state table itself. Now we can do 2 different kinds of assignments. So clearly there are only 7 states, and for 7 states we need 3 flip flops first of all. So we have 3 flip flops. We can do different kinds of assignments. So in assignment 1 we are going to try this. For A we are going to assign 0 0 0, for B we are going to assign 0 0 1, for C 0 1 1 and so on. And assignment 2 we are doing something else. So let us not worry about how this was arrived at. So if you are not given anything, if you do not know how to do it carefully, then you may come up with in fact any random assignment, right, any random assignment, as long as each of the states gets a different vector, that is actually a valid assignment. So we have 2 valid assignments here, none of the states repeat within the assignment. For different states we have different assignments. So this is what I call by the state assignment. So these are 2 different state assignments, and let us see the implication of the 2 state assignments on the hardware that will get generated. So we will assume that we are using JK flip flops in this example. Using assignment 1, the circuit seems to take J1 equals this, J2 equals this and so on. So again, without questioning how this was arrived at, I believe you know the process for that right now, and let us also believe that it is done in the most optimal way. Then the assignment 1 seems to have these equations and assignment 2 seems to have these equations. So you compare assignment 1 and 2, just by looking at the equations you can probably say that assignment 2 seems to be a bit complex. Whatever the definition of complex is, it seems to be a bit complex. Let us go and validate that by counting the number of 2 input AND gates, OR gates and so on. If I look at the 2 input AND gates, so there are 4 inverters, there are 7 AND gates and 1 OR gate, which makes a total of 14 gates, and here there are 4 NOT gates, 11 AND gates and 7 2 input OR gates, making a total of 22 gates. So you have 14 gates here and you have 22 gates here, and the choice that we made, instead of using assignment 1 we use assignment 2, you suddenly have a gate count which is greater than this one and almost 50% greater than the previous assignment. So the key thing is, coming up with a state machine is one thing. Given a problem you can come up with a state machine, and you can also do state minimization and reduce the number of states, right. So let us assume that that actually happened here. Let us assume that the state machine is already minimized, we cannot go to anything lesser than 7 states. So that is the case for this circuit here, this state diagram here, it cannot go to lesser than 7. The choice of which assignment we are going to make seems to make a difference in terms of the number of gates. So in summary, there are two things which can change the total number of gates. This could either be the state diagram that you draw itself and the associated minimization that you do with it. If you come up with a bad state diagram, or if you do not minimize, that can actually increase the number of gates. Second, even if the state diagram is minimized and whatnot, the state assignment that you do can actually impact the number of gates. So we already addressed the first problem in the previous lecture, we will look at the second problem in this lecture. So the key thing is, how do you do this assignment carefully? If we look at S states in a state machine, and let us assume that it requires n flip flops. So if I have S states, typically you need n in such a way that it is logarithm of s base 2 and the integer that is just greater than that. So if I take 2 states, I require only 1 flip flop, and there are 2 possible assignments. Let us say I have states S0 and S1, then there are 2 assignments that are possible. I will label the S0 state as 0 and S1 state as 1, or the S0 state as 1 and S1 state as 0. There are only 2 assignments, so it is not a big deal. In fact, you may actually try both these assignments, see which one gets the least amount of hardware, and you can stick to it. Let us try and make it slightly larger. If I have 3 states, for 3 states you will require 2 flip flops, but the number of assignments goes to 24. So by the counting that I am doing is, if I have S0, S1, S2, what are the different ways in which I can label them? So I could assign S0 as 0, S1 as 1, S2 as 2, or S0 as 2, S1 as 3, and S2 as 0. There are several assignments that are possible. It looks like there are 24 assignments that are possible. And now if I want to find out the smallest number of gates, then you may still be able to do it. You have 24 assignments, you try all the possible 24 combinations. It's a bit of a laborious work. You do all the 24 combinations, you may still come up with the least number of gates. However, it quickly gets very ugly. If I have 6 states, then you need 3 flip flops. So the 3 flip flops actually can represent 8 states, but you have only 3 states, only 6 states that are being used in the 3 flip flops, and the number of assignments that is possible is 20,000. So this is already infeasible, you cannot do this exhaustively, and this gets very ugly when S and N increase. So if I have 8 states, then it requires exactly 3 flip flops, all the states will be complete, all the bit combinations will be used, and that seems to take 40,000 assignments. So you have to pick one among these assignments which is the best and use it, and if you increase the number of flip flops to 12, 16 and so on, it is already going into billions and trillions. In fact, in a real world machine, the number of states is not even 16, it could be much larger than this. So we are talking about hundreds and thousands and so on, and if you have something like that, the number of flip flops that is possible will also be in the tens and hundreds, and number of assignments is, you cannot exhaustively search. So the key thing is, you cannot exhaustively try all different state assignment combinations and pick the best one. In fact, you do not even do it manually. So even if you do it with a computer, it is still too many assignments and you cannot finish this in any reasonable time. So the state assignment problem is, it is not practical to go through all the possible combinations either manually or using a computer, and unfortunately there is no easy way in which you can determine this. So this notion of optimal state assignment, the state assignment which brings you the smallest number of gates, unfortunately this is not something that you can do, there is no simple technique to do this. What we need is, we need what are called reasonably good assignments. We do not, as long as we follow some principles and come up with some way of solving this problem which is only reasonably good. It may not be the best way to do it, but it is a reasonably good way to do it. As long as we have that, then such guidelines are useful in minimizing the amount of hardware. So what we are going to do is we are going to use what are called heuristics. Heuristic is essentially more like an intuition or an idea that it might work, but without any guarantee. So for instance, when you drive from, let us say, your home to the railway station, you may have an intuition that this road is better than that road, this road gets more traffic than that road and so on, and based on that you may actually take a decision. But this decision need not be the best decision because you assume that some road is not going to be with traffic, you go there and suddenly there is traffic because of some accident. So such things, right, you cannot do anything about. So in this case the word heuristic, I am going to use that to indicate that you come up with some reasonable intuition about doing a particular kind of assignment is going to actually help in reducing the number of gates. And the heuristic, as long as there is some bit of engineering principle in coming up with the heuristic, it might help in reducing the number of gates. So the heuristic cannot be I will come up with a random assignment, that does not that there is no intuition about how to minimize the number of gates in that. However, if we use what is called a bit change heuristic, what we are going to do is we are going to look at the states and we are going to force large groupings of logic ones. So I will show you a quick example in the next slide. So we know this from the K maps. If I have ones that are closer to each other, then you can group them and reduce the number of gates, right. We are going to try and do something very similar with states. So what we are going to do is we are going to have a set of guidelines. The guidelines are based on this. So we are going to have guidelines based on the next state and the inputs and outputs. So the highest priority of grouping would be given to states with the same next state for a given input should be given adjacent assignments in the state map. So if I have a state with the same next state for a particular input, so if I have a single bit x equals 0 and x equal to 1 or 2 possibilities of inputs, on the next state for a given input, if you go to the same state, they should be given adjacent locations. Medium priority is next states of the same state should be given adjacent assignments, and the lowest priority is states with the same output for a given input should be given adjacent assignments. So this picture will help you in understanding what I mentioned in the previous slides. Again, we will use this in an example later. Let's look at this picture here. We have two states alpha and beta, and alpha and beta, both of them on the input I is going to the state called epsilon. So there are two states on the same input, they are going to a state called epsilon. What if you have cases like this, you would want alpha and beta to have state assignments which are close to each other. Then if you have a state like this, if you have a single state, let us say on one input you go to alpha and the other combination of input you go to beta, then you would like alpha and beta to be neighbors of each other in the state assignment. So by neighbor they should have bit positions which are only a few bits different. And finally, if you have two different states that go to two different states, but they have the same input output combination, then you try and assign alpha and beta to adjacent states. So this notion of adjacency means if I take the bit vector assigned to alpha and if I take the bit vector assigned to beta, the number of bit flips that you have to make in the bit vector of alpha to get the bit vector of beta, that is called adjacency. So if you are given two different states, at least there should be one bit difference because you want two different states to have two different state assignments. If the assignments differ by exactly one bit, then they are adjacent. If they differ by 2 bit positions, then it is one more distance away and so on. So the case I was making was if alpha and beta are actually two different states which are heading to the same state, then the binary assignment of alpha and the binary assignment of beta, you should have them in such a way that they are very close to each other. The number of bit flips that you should have for such cases should be minimized. So let us see these guidelines. These are only guidelines, these are not rules, these are guidelines. Let us see how to use the guidelines. So I have put this picture here so that we can use this in grouping and so on. So let us start with this state diagram. we have 4 states A, B, C, D, and it will use 2 flip flops. There are several ways in which you can assign the states to A, B, C and D, and we want to see how to assign it the best way. So what we will do, so what we want is for A, B, C and D, we want the combination 0, 0, 0, 1, 1, 0 and 1, 1 assigned. Let us see how to do that. So let us go and look at the highest priority. Highest priority says if there are 2 states which are both going to the same state on the same input, try and make them closer to each other. You go and look at this setup here. If you see at x equal to 0, there is C/0 and C/0. So from state A and state B, on input x equal to 0, we seem to go to the same state C, right. So if this is A and this is B, we are both going to the same state C on the same input x equals 0. In this case, the outputs J and K also happen to be the same, right. So what we would like is, we would like A to be a neighbor of B, because if you do that, then the number of bit flips you require to go from here to here and here to here will be minimized. Then for x equal to 1, if you notice, there are 2 states A and C, both of them go to the same state D. So we would like C also to be close to A in the bit assignment. Let us look at the medium priority guidelines. So from a single state, if you have 2 different states which are neighbors of each other, we would like them to be closer. So from A, D and C are the neighboring states, we would like D and C to be closer. From B, A and C are the states to which you are heading out. From B, you have x equal to 1 goes to A, x equal to 0 goes to C. We want A and C to be neighbors of each other in the state assignment. With respect to C, it is D and B, with respect to D, it is B and A. So some of these affinities are already captured here also, but it does not matter. So sometimes you may also have the affinities to be the same. So what we have is, we have from the medium priority guideline, we have these affinities. And finally from the low priority guideline, the low priority guideline says if you have 2 different states and if you get the same input comma output combination, then you go to 2 different states, you do not care about whether these are adjacent or not, you make alpha and beta to be adjacent. So you go and look at x equal to 1, then they at x equal to 1, A, B, C, all of them produce 0. So with respect to x equal to 1, you want A, B, C to all be neighbors of each other, and with respect to x equal to 0, again A, B, C states all of them have output 0, you would want them to be neighbors of each other. So in this case, the affinities that we are getting seem to be the same. Now we have these affinities. Given these affinities, we have still not made any assignment. We want to make an assignment in such a way that the states A, B, C and D follow these affinities as much as possible. Not that you can always follow it, you want to follow it as much as possible. So let us look at all these adjacencies. So this is from priority 1, this is from priority 2 and this is from priority 3, and we are going to do the state assignment in such a way that the highest priority things are taken care of first and so on. So let us do one assignment first. So since these are 4 states, what you do is you first draw a 2 variable K map. So a 2 variable K map will have 2 flip flops Q2 and Q1, right, and in that you mark 0, 1 and 0, 1. You start with one of them, right, you start with this one for instance, you put A in one of these positions. What this guideline says is B and C should be adjacent to A. So in this assignment you have A, and if you go and look at B, B is closer but C is not, right, whereas in this assignment C is closer but B is not. In the third assignment C is closer as well as B, right. So with respect to the first priority, this seems to take care of both the priorities, whereas these two do not. Then let us look at the next set of assignments, CD, AC, BD, AB and so on. So you go and look at each one of them. Is CD close? Yes. Is AC close? No. BD close? No. AB close? Yes. So of the 4, 2 of them are satisfied. Let us go and look at this. Are C and D close? No, because they are they are not neighbors of each other, you cannot group them. If these are two ones in a truth table, you will not be able to group them together, right. So these are not close to each other, AC yes, BD yes, AB is not. Finally, if you go and look at this, CD yes, they are neighbors of each other, if these are both ones I can group them, AC I can group together, BD I can group together, AB I can group together. So it looks like assignment 3 is good even with respect to the second priority. With respect to the third priority, A, B and C should all be close to each other. These are three different states, clearly you cannot group all of them together into one thing. So as long as A, B, C are neighbors of each other, that will work. In this case, whatever you do, right, they will be neighbors of each other. So in all of them we have A, B, C, which is a continuous thing. So in the lowest priority is actually not useful in this one. Let us look at the assignment. This assignment seems to have the best, so it complies to these adjacency priorities the best. So this assignment, if we do, if I assign 0 0 to A, 0 1 to B, 1 0 to C and 1 1 to D, then that seems to give the best result for this particular state machine. So what I would like you to do is go and try out for assignment 1 and assignment 2, go and figure out the number of hardware, the hardware units, how many AND gates and OR gates are required for each one of them. Compare that with what happens when you have assignment 3, you would notice that assignment 3 actually has the lesser gates. So the reason why we want them to be neighbors of each other is that if they are neighbors of each other, later when you go and derive the next state and so on, you will be using these bit positions, ones and zeros and so on, they will become close to each other. So if you go and look at the next state logic or the output logic, so these are combinational circuits, right. In these combinational circuits, states which are close to each other in the table that is shown here will put ones in the truth tables when you do the combinational minimization. That is the reason why we want to follow this heuristic. So let us see a more concrete example, a bigger example. So let us say I have a state machines with 8 states and I want to be able to do state assignment for this. So again the priorities are given below. So let us start with each one of them and see how to do this. So let us start with the highest priority guideline. Highest priority guideline says, are there two states which are coming into the same state, right. So you go and look at this with respect to x equal to 0, you go and look at, are there states where you are coming in with x equals 0 itself. So you look at D has an input with x equal to 0 and F has an input with where x equals to 0, and if you go and look at G has no input with x equals to 0, E seems to have something with x equals to 0, C does not have, B seems to have something and so on. So if I have two different states that are converging into the same state, so let us look at this, D and E, you look at D and E, both D and E on 0 is going to F. So we would like D and E to be neighbors of each other. Similarly, if you look at F and G, on 0 they both seem to go to A. So we would like F and G to be neighbors of each other. In fact on 1 also they seem to go to the same state A, so we want F and G to be neighbors of each other. This is the highest priority. The medium priority is the case where from a single state you are branching to two different states, you want them to be close to each other. So for state A, from the states A perspective you want B and C to be closer to each other, from B and C's perspective you want D and E to be closer to each other, and from let us see, from D's perspective it is only going to F, on both 0 and 1 it is going to F, so there is no problem. From E's perspective you want F and G to be closer to each other, from F's perspective you are anyway going to A on both the transitions, on G you go to A on both the transitions, so these are the set of preferences. So this D comma E would come twice, once because of B and once because of C. Finally, in terms of grouping similar outputs and input output combinations, if you look at 0 0 combinations, then A, B, C, D, E, F should all be together because they all have outgoing transitions which are 0 0. So you look at A, it has a 0 0 transition, B has a 0 0 transition, C has a 0 0 transition and so on, whereas F and G, so G does not have a 0 0 transition, G has a 0 1 transition. You would like all these to be neighbors of each other with respect to 0 0. With respect to 1 0, it looks like all the states have a 1 0 transition going out, so all of them have to be neighbor of each other. So you may not be able to satisfy this. Let us see how to do an assignment based on this. Again, the adjacencies are listed here. Let us see how to go about doing this in a step by step manner. So let us start with an assignment. In this case, there are 7 states, we need 3 flip flops. We start with a 3 variable K map. We pick a state arbitrarily. Let us pick some state arbitrarily. I am going to put that at 0 0 0. So I picked A arbitrarily, I put it at 0 0 0. Now I am going to look at what are all the affinities for A from, so there is no high priority affinity of A. In the medium priority, A and B has to be closer to each other, right, we want that. So I will not satisfy that right now because that is not the highest priority affinity. Instead I go and look at the highest priority affinity, I see that D should be closer to E. So however, D has no affinity to A, so you go and look at this, A should be close to B in the medium priority, right. So I will not place D in the neighborhood of A, I am placing it away from A. So if I take this A, this cell and this cell are all neighbors of A, I am not placing D in any of those. So I could place D here, D here, D here or D here, I am taking D to be here. And from the highest priority I want E to be close to D, so I put that close to each other. And then the other one that is left out is F comma G. So if you look at F comma G has no particular affinity to A, D or E. In all these things, F and G, say F and G have to be close to each other, but they do not have affinity to D, E. Similarly, F and G by itself is there is no affinity to A or D comma E. The only thing is, in this case we see that out of F and G, F should be closer to E, A, B, C, D and so on. So one thing you can do is, you can do an assignment for F and G here. So F is still close to this D, E thing. For G there was no affinity that was asked for, so G happens to be close to F, that is all. Now B and C are still left out, we want B to be closer to A. So there are 2 slots in which I can put B, I pick one of them arbitrarily, and a C could either be here or here, again I have picked C arbitrarily. So you can see that there are lots of arbitrary things that I have done here, it is not all decisions that are all very careful. The only decisions that were careful are that DE must be separate from A because there is no affinity to A, and D and E are neighbors of each other, and similarly we decided that F and G could go anywhere, it could go into any of the positions, we decided that arbitrarily. The position of B was arbitrary, the choice of A, the very first thing that we picked itself was arbitrary and so on. This is one of the assignments. Let us look at the state assignments. I now go and read Q3, Q2, Q1, right. So I go and read the state assignment. So for E it is 1 1 1, for G it is Q1, Q2, Q3, so it is 1 1 0 and so on. That is the way in which you can get state assignment. There are other assignments possible, so I will show you another assignment now. So you start with A, which is here, now you go and look at the next set of assignments, it looks like F and G, right, and F has some affinity to A in these 2 cases, I put F and G here. We still have D and E and D and E, so I put that here and I put B and C as it was before, like this. So this FG choice, remember it was arbitrary, right, I put F and G here, and if I do this, the state assignment seems to be this. So both these assignments actually satisfy all the high and medium priority guidelines as well as the low priority guidelines. If you look at A, B, C, D, E, F, G, they are all neighbors of each other. A, B, C, D, E, F is also some continuous chunk, A, B, C, D, E, F is some continuous chunk, A, B, C, D, E, F is some continuous chunk, and G happens to be separate in each one of those. So this is one assignment. So for each of these assignments you can go and try out the number of gates and see whether this one reduces the number of gates or this one reduces the number of gates. I would like you to do this as an assignment yourself. So this is again a 7 state machine, and these are the state transitions. I would like you to use the heuristics and come up with an assignment possible for this. So in this whole setup it is possible that there are unused states. So if I have n flip flops, it can actually represent 2 power n different states, but you may not have 2 power n different states, you may have only s different states, in which case what happens is you are not using all the possible combinations of the flip flops to represent a valid state. So these unused states or the unused state vectors are a problem. So in the previous example here, the vector 0 1 0 is not assigned to any state in this assignment, the vector 1 0 0 is not assigned to any state in this assignment. So these are unused states. When you look at these unused states, they can cause a problem. So there are two approaches to deal with unused states. One thing you can do is you can do what is called the minimal cost approach. The minimal cost approach, you assume that the machine will never enter an unused state by any mistake, and you put a don't care wherever you see an unused state. So if you want to reduce the overall cost, the unused states are all marked as minimal cost. So this is okay if you know that under no circumstances you may actually enter into a illegal or an unused state. So remember, the moment you go into a state which is unused, there are no transitions specified for this, right. So at x equal to 0 and x equal to 1, you do not know what to do there. If you know for sure that you will never enter that state, then we do not have to worry about how to leave the state. So that is the low cost approach, the minimal cost approach. Then there is this other approach called the minimal risk approach. Here what you do is, by accident, if you somehow end up in the unused state, you put some state transitions there in such a way that you get to some known state. So both these things have issues. So minimal cost and minimal risk, both of them have issues, but the primary reason why something like this can happen is that when you power up the circuit, for instance, you may not know what the values of the flip flops are. You should not assume that when I turn on a chip, automatically all the flip flops will be zeros or will be ones and so on. We cannot assume that. So the flip flops may actually open up or start in any which state, unless you actually put an explicit reset so that you bring all the states to some known condition. This may be a problem. So typically what you do is, as a good design philosophy, you go and have an explicit reset state so that you power on the machine, you do a reset so that all the flip flops start with some known values, and if you do not do that, it is possible that you can start the circuit in an unused state. The other reason why you may enter into an unused state is that there is some problem in the circuit, and it could be because of a timing violation more often than not, that a flip flop is supposed to be, so you are supposed to go from a clean state A to clean state B, however you go through some transition and you get stuck somewhere in the middle. So this can happen, and we will see some of these design issues and philosophy behind how to design state machines in a later video. But there are two ways in which you can handle unused states. Either you can treat the unused states as don't cares, or for each and every unused state you go and put explicit transitions so that you actually end up using it. There is one final thing that I want to talk about in state assignment, that is the notion of one hot encoding. So far we have been looking at what is called a dense encoding. In a dense encoding, what we do is, the number of flip flops that we use, we want to be stringent about that. We want to use as few bits as possible to represent the states. One hot encoding is an alternate approach. What we do is, we use as many flip flops as there are states. If I want a n state machine, instead of using log n flip flops, I will use n flip flops, and we will do what is called one hot encoding. One hot means at any point of time so we know that the state machine should always be in exactly one state at any point of time, right. So whatever inputs you give and so on, your state machine can be in exactly one state at any point of time. this exactly 1 means it can be in at most one state and it should be in at least one state. That is what gives you exactly one state. If you want to reflect that, you come up with n flip flops and you have to give a guarantee that exactly one of these flip flops will be on and all the other flip flops will be off. This is called one hot. So in one hot encoding, what you do is, for a machine with n states, you use exactly n flip flops, and the one hot condition is that each state is represented by a n bit binary code in which exactly one bit is asserted. So let us see the example here. So for the same picture that I showed earlier, this is the state diagram, and for binary encoding we have to do a lot of heuristics and so on, right. Instead here what you do is you come up with one hot assignment. So there are 7 states. The first thing you do is you put 7 flip flops q1 to q7, and if you want to represent the case you are in state q, you are in state 1 which is for A, we assign q1 equals 1, we assign all the other flip flops to 0. So this state assignment we associate with A. The assignment 0 1 followed by all zeros, we associated that B, and we give for each one of them some combination. So it's in this case F happens to be 0 0 1 followed by many zeros, G is many zeros 1 0 and so on. If you notice the state assignment here, all of them are one hot. There is exactly 1 1 and all the other combinations are 0, and the state assignment also requires that you cannot have the same state vector for 2 different states. So we do not have that here. So this is called a one hot encoding. The nice thing about one hot encoding is that if you inspect a particular flip flop, you can say that you are in that state or not. So if at any point of time I give you the state register, you can go and see what is the one, and you can tell me that you are in that state and not in any other state. So there are lots of uses because of this one hot encoding. So if you go back to binary encoding, right, you have the canonicals, you have the state register which in some sense is compressing. So let us look at the picture here. You have a state register, right, this uses log n flip flops for n states. You have some input forming logic and some output forming logic. So the current states and the inputs form the outputs, the current states and the inputs form the next state. So this is the input forming logic, this is the output forming logic. So because you have encoded it densely, when you have to go and do things like for this state then the output must be 1 and so on, technically you are actually decoding it here within this circuit. You decode here and you decode here because you have encoded the states here. Whereas when you do this in one hot encoding, you actually do not do that. So there is something nice that happens in one hot encoding. In one hot encoding, the decoding is actually simpler. If you want to find out if you are in a particular state, you only inspect that bit. So if you want to implement this using D flip flops, I go and look at D1. So I want to look at what are all the conditions at which Q1 should be on. For the dense encoding, it seems to be some complicated equations, right. So I have to go and derive it, I have to put it in the K map and so on. Whereas if I want to go and look at each one of these conditions, so you go and look at this, D1 should be on when either Q3 or Q6 is on. So what that says is, if you have, so you go and look at A, what are all the conditions under which you will come to A? You should be in either F state or it should be in G state. So go and look at F state. At F state you have Q3 is on, G state you have Q6 is on. So if either Q3 or Q6 is on, the next state you will go to A. That is what this means. Let us go and look at D3 for instance. So we are looking at state associated with Q3. So let us look at the state as F. F is the state associated with Q3. Let us look at all the combinations in which you come to F. If you are in D, you go to F, whether it is 0 or 1 you go to F. But if you are in E, if the input is 0 you go to F. So this is something you can derive by looking at what is the state assignment for D. For state assignment D we have given Q4, for state for assignment of E we have given Q7. So, if Q4 is on, no matter what x is, you will come to F. So, that is Q4. If you are in Q7 and if the input is x, input x is 0, then you come to F, that is captured by Q7 x bar. So, by just looking at the picture without doing any minimization, I can write these equations down. You do not have to do anything at all, right. And if you go and look at the outputs, let us go and look at the circuit where the output is. So, it seems to be that the output, let us see where the 1 is, here. If you are in state G with x equals to 0, you are producing output of 1. You go and look at the state assignment for G, that is Q6. So, if you are in Q6 and if the input is 0, which is x bar, then the output must be 1, that is all, right. So, it is as simple as that. For there is no decoding at all, the decoding is as simple as looking at a particular bit position and inspecting whether it is 1 or 0. So, what we have is a very nice encoding mechanism, and you do not have any logic at all. Even though you have used a lot more flip flops, the amount of logic that you use for decoding is very simple. So, sometimes this one hot encoding is preferred over dense encoding, because the decoding logic, so every time I have to inspect which state and so on, it gets reduced. So, this is much nicer, especially when you use what are called FPGAs. FPGAs have a lot of flip flops. Doing one hot encoding is actually preferred in FPGAs compared to other techniques. So, this brings me to the end of this lecture, and in module 32 we saw state assignment and we saw quite a few heavy duty things in module 32, and I suggest that you go back and work on the examples. I have been repeating this in every video. I suggest that you go back and look at the examples. Until you do that, you may not get all the concepts right. So, I am showing you one example. Unless you try other examples, you may not get all the concepts right, and if you do not understand something, please come back on the forum and do ask questions on the forum about these examples or something that you make up. So, thank you, and I will see you in the next module. Bye bye.